All right, thank you. So first I'm going to do a little bit of motivating why we should care about ion escape at all and why you should listen to the rest of my talk. And that's because while light species like hydrogen can escape thermally, just in that the tail of the velocity distribution it can exceed the escape velocity, heavier species need additional energy sources and able to have that escape be any sort of real factor in atmospheric evolution. So things like carbon dioxide or oxygen. Ion escape is important because one source of that additional energy can be electric fields. And we know that ion escape plays a key role at Mars, and I'm sure we'll hear more from Bruce about that later. And it's observed occurring in all terrestrial solar system planets today. So my project here is to think about how do we transition our knowledge of how ion escape works in the solar system to exoplanets. And in general, I'm using Mars as my sort of base case, and then using a hybrid plasma model to understand how this ion loss processes will change if I consider a Mars-type planet around an M dwarf instead. So the factors of stellar influence that I'm concentrating on here, the first is that M dwarfs have enhanced EUV compared to the sun, and we know this from many stellar surveys, which find that factors of a few to a couple hundred times the flux in the EUV for M dwarfs. I'm also going to look at how the stellar wind will change. We expect increased solar wind pressure, both magnetic and dynamic pressure. We know this from solar wind reconstruction models that are inputs from mass loss observations of other stars and Zeeman Doppler imaging of the magnetic field. And so from these, we expect that we are increasing both of those factors. And then finally, I'm going to look at the influence of the interplanetary magnetic field from Parker-Spira models of how the interplanetary magnetic field extends throughout the solar system. We know that nearby a star, it's more radially oriented, but as you move out to greater distances, it starts to bend so that the magnetic field is more perpendicular to the velocity vector of the solar wind. But because M dwarfs are dimmer and the corresponding habitable zone is much closer to the star, we know that the IMF is much more likely to be radially oriented or parallel to the direction of the solar wind velocity. In the future, I'm going to look at how these results will change with different planetary parameters, but right now just focusing on a Mars-type planet to start with. So the simulations I'm going to be showing are using the R-hybrid model, which is a global plasma model where the ions are treated as macroparticles and the electrons are treated as a fluid. So that allows you to include ion kinetic effects, which are important in many cases. And this is a model that's used to model ion escape at Mars and at Venus, Titan. And the one other simulation parameter that I want to point out before moving on is that the ions in this model are injected using Chapman profiles. So this is just a spatially varied with solar zenith angle ion injection method. I'm not actually simulating the ionosphere or doing any sort of ray tracing to talk about the EUV. I'm just setting a specific method for injecting ions. All right, so I've run 5 different simulations where I'm trying to slowly move from what we expect for the nominal solar wind at a Mars planet to this total model of a planet around an M dwarf. So starting off, my first simulation is just the nominal solar wind. And then I changed the IMF to be parallel and just changing the angle, but keeping the overall strength the same. And then keeping this parallel IMF, I then increase the total pressure, so both the magnetic pressure and the dynamic pressure, but keeping the ratio between those two the same. Then I increase the density of the solar wind by a few orders of magnitude, which also increases the ram pressure. And then finally, I increase the EUV, but I don't actually increase any sort of EUV photon flux. I'm just ramping up my ion production. Okay, so the first result that I want to talk about is how the IMF orientation affects things. So on the left here, I have my nominal case, and on the right, I have my quasi-parallel case. And you can see that the left, everything in the bow shock, I'm showing H plus number density and velocity, looks very symmetric and nice. But when you move to the right, things get a little crazier. And that's because a shock is unsteady if the angle between the shock normal and the magnetic field is less than 15 degrees. And so for a quasi-parallel interaction, that's satisfied for an entire hemisphere of the shock. This means that kinetic effects are becoming more important because we're in this unsteady regime. And there we go. It means that the solar wind velocity can approach the ionosphere at a much higher velocity in this unsteady hemisphere. So you can see down here where the H plus gets shocked in the nominal case, but because it's unsteady, it approaches at a much higher velocity in that corresponding hemisphere. This drives asymmetric ion outflow because of this asymmetric shock. In our Mars type case on the left here, all the field lines approach from right to left and drape symmetrically around the planet and cause ions to be accelerated in the direction of the motional electric field that's just up in what people who work on Mars like to call the plume, and it's often referred to as sort of a mohawk coming out of the top of the planet. Whereas now, in our parallel IMF case, things are only accelerating off of this one side of the planet, and now we are in more of like a side ponytail, some would say. These ions then continue to be collimated by this the draping of the magnetic field lines, where they're kind of in a U symmetric shape behind the planet, but they're kind of an S looking thing over here, which drags them off towards the left. And this is really interesting because if we're only accelerating ions from one side of the planet, it could introduce or enhance atmospheric asymmetries at lower altitudes. And this is probably especially important for tidally locked planets where one side is always facing the sun. Okay, so now looking at my next simulation, where on the left I have parallel IMF case, and on the right we've increased the total pressure but kept that parallel IMF. Over here, all of the ion motion seems very coordinated, essentially. And that's because the ion gyro radius, as is typical at Mars, is a couple times the size of the planet. But in my right-hand case, everything kind of looks smeared out because although I increase both the solar wind velocity and the magnetic field, I increase the magnetic field a lot more, making this ratio, defined as the ion gyro radius, much smaller. And so you don't expect to have coherent motion on the size of the planet anymore. This means that where on the left we have plume escape and tail escape as two distinct channels, now everything's kind of this mushy blob. And so it'll be really important when we're applying knowledge from how different escape channels scale with different drivers from our knowledge at Mars to exoplanets. We have to be very careful in how we define these different channels and maybe not just use spatial location, but use how ions are originally accelerated as our definition. I'm going to skip ahead. Instead of showing every single slice plot for the rest of the simulations, get to the cool part where we talk about ion escape globally. But instead of talking about just rates, I'm focusing on relative escape rates here. This is because overall escape rate for these simulations is really sensitive to how you inject the ions, and we have no observations of atmospheres of Mars-type planets around M dwarfs right now. So I'm really just interested in comparing to my Mars-type case to start with. And you can see that for each run, the escape rate tends to increase, except for this transition from R2 to R3, where I increase the solar wind density. So even though I'm putting more energy into the simulation, I'm not driving any more escaping ions. And this is because because we become in a production or diffusion limited regime where in these cases 50% about of all of the ions I'm injecting into the simulation escape. And so even though you're putting more energy into the simulation, you don't actually drive any more of them escaping because it's just harder to find ions to start to escape. And this is really interesting because a lot of what we're looking at it scaling from a Mars type case to exoplanets is kind of extending how the escape works with different solar wind drivers. But this points out that we need to be careful in considering those limitations because they're not going to scale indefinitely, and we're eventually going to run into limits that we don't see in our current solar system case. This is true again when we think about how energy escape coupling works. It's a very astrophysicist kind of view of things where energy in should couple to energy out with some sort of efficiency. And so that's what I'm showing here. Energy in, there's solar wind power, energy of escaping ions out on the y-axis, and then these constant lines here show some sort of constant efficiency at which we're driving escape. And our nominal conditions, shown here by this dot, actually are the most efficient energy coupling between the two cases. And that's because, again, we are production or diffusion limited in some of these more extreme cases, so we just don't transform energy input from the sun to escape in as efficiently in those regimes. Cool. So in conclusion, the stellar input parameters are influencing both the morphology and the escape rates that we see in this simulation. It's important to consider the definitions of our specific processes when we're trying to think about how to transfer things from the solar system to exoplanets. And asymmetry is going to be a big deal, especially in these quasi-parallel cases, which are going to be likely for M-dwarfs. And limiting cases are also going to be important, particularly in how ions are produced. And in the future, I'm going to talk about how this will all change when we have magnetic fields at our planet. But for now, unmagnetized. Thanks.
Great. Thank you very much. Do we have any question right here?
Hi. Real quick question about your point about loss asymmetry may have implications for the atmosphere. You mentioned that earlier. You're saying that the loss of essentially mass out of the atmosphere can impact the dynamics or the circulation of the underlying atmosphere?
More so I was getting at just that if we have some population of oxygen, for instance, and if we're losing half of all of the ions there, I could see some sort of maybe not overall mass difference in the atmosphere, but species difference that could affect things.
Oh, so it would still affect it in terms of just a gradient of species rather than like a mass pressure gradient or something like that.
Exactly.
Okay, thank you.